Lesson 9.1c is going to introduce us to multiplying and dividing radicals. So that actually should have an S here on the end. Multiplying and dividing radicals. And the multiplying piece of this is actually not new. You didn't formally know it, perhaps, but you really have been using the product property, which is multiplication, right, of square roots every time that we did that simplified radical. So you already probably intuitively knew that if you had something under the radical, you could take the square root of each one individually. What's going to be slightly different about the way we tackle that today is that we're actually going to go in this direction when we're multiplying. But in using it in simplifying radicals, we already knew this relationship to be true. That if the product of if the square root of the product of two things was there, you could take the square root of each factor. We're just going in this direction when we multiply, where if we have them separated, or we know we have the square root of two quantities, we can take the square root of their product, okay, and get that. And then we still, of course, always simplify. So if we square root of 10 times the square root of 6 here, can then be the square root of 6 times 10, which is 60. And once you know what that product is, then you make sure that you pull any perfect squares and leave your answer in that simplified radical form. So we'll practice that a few times, but it should already be familiar because we've been doing that process basically like this, right? We've been doing that process in our simplifying. We're now just going to use it for multiplying. So what I want to talk a little bit more in detail about in this lesson is the quotient property of square roots and doing something that we call rationalizing our denominator. Okay, so the first part of the quotient property states that we can take the square root of the top and the bottom. We've also done quite a bit of that as we were simplifying. Even on the practice on the very first lesson, simplifying radical expressions, we knew that we had the square root of a fraction. We could take the square root of the numerator and then the square root of the denominator. Okay, so then what I really want to talk about is this concept right here, rationalizing the denominator, which basically states, it's just one of those rules in math, that in addition to taking the square root of the top and bottom, we never want to leave a radical in the denominator. It's just a no-no, okay? It's not a proper format, and you'll always want to make sure that you clear that. So even after any simplifying and so forth, if you end up with a square root like this in the denominator that you know you really can't get rid of any other way, this is where we will rationalize the denominator. Write it down. So how do we do that? Well, we want to get rid of the radical. And in all of this practice, hopefully you've realized or you've concluded that what allows us to drop the radical is when we have a perfect square, right? So if I have a perfect square, then I can drop the radical and, take that square root and drop the sign. So that's really what we want to achieve when we rationalize the denominator. If I have square root of 3, which is not a perfect square and it is already simplified, but I know I'm not allowed to leave that radical down there, then the game begins to try to multiply that 3 by something that is going to generate a perfect square. For squares, that's really easy. You can just multiply it by itself, and that'll always get you where you need to go. So it doesn't always have to be times itself, and we'll see a few examples of that in a little bit later. But if you have square root of 3, we know that as long as we multiply by another 3, that will automatically give us a perfect square, and then we will be able to take the square root of that and drop the radical. Of course, like everything else with fractions, if we do it on the bottom, we also have to do it on the top. So that's the catch, right? But that's okay because we ought to leave radicals in the numerator. We're just not allowed to leave them in the denominator. So to get rid of that square root of 3, we multiply by another square root of 3 on top and bottom. So on the top, we now have square root of 30. But the good news is, on the bottom, square root of 3 times the square root of 3 is the square root of 9, and that is a perfect square that lets us just drop that radical when we take the square root. That's called rationalizing the denominator, and it's probably the most sort of key feature of today's lesson that you want to make sure that you're comfortable with after we practice and so forth. So that's really that whole lesson. It's just the multiplying and the dividing properties here. Let's start off with a little bit of multiplication practice, and then we'll go on to the division. So let's start with multiplying. So we want to write each product here in simplest form. We want to multiply it and then leave our answer in that simplest radical form. So no decimals here, okay? So we'll start off by using the property that we just talked about. If square root of 3 times the square root of 12 are being multiplied, we can simply take the square root of their product under the same radical, which we know 3 times 12 is 36. And then we want to make sure we simplify that. It does happen that 36 is a perfect square, so this answer is just 6. Nice and easy, okay? How about number 2? If we've got the square root of 10 times the square root of 5, that's really the square root of 10 times 5, which is 50. And then we simplify if possible. 50 is not a perfect square, but we do know it breaks up into a perfect square 25 times 2. So we can separate it back out into these proper factors where we can pull that perfect square, make it a whole number 5, and just leave the 2 in the radical. And that is the product of these written in simplified radical form. Okay. On number 3, we have a little bit of numbers on the inside and outside. That's kind of like terms and so forth. We can work the numbers on the outside together and work the numbers on the inside together. So if there's nothing in front of you, you can think of it as a 1. 3 times 1 is still going to be 3. In other words, the 3 is just going to stay. Okay. We cannot multiply a whole number times what's inside. That's why we leave these separate like that. So the 3 is just going to stay. What we can multiply together is radicand times radicand, which is the part that's on the inside. Those are both underneath the radical, so those I can multiply together and do my 5t here times the 40t, and then multiply that together. The 3 is still on the outside. This is going to give us 200, and then t times t is t to the second. Okay. And that looks pretty good, except we want to make sure it's simplified. And I definitely know there are some perfect squares that go into 200 and t squared. So probably the easiest one here is the 200. We know breaks up into 100 times 2. And then t squared is already a perfect square because it's an even power. So this one's still outside, but we can take each one of these roots separately. Okay, so the 3 is hanging out. The square root of 100 is 10. I'm going to kind of bring this guy over because it's a perfect square. The square root of t squared is just t. And then this guy, the 2, is not a perfect square. That's really the only thing that's going to stay inside. Once you have taken all the square roots you can, if you have like factors, do clean that up. So this 3 times 10, we can definitely clean that up and do 30 there. So really our final answer here is 30t. That's all nice whole numbers that were able to be pulled out of that radical. The only thing that had to stay in was that 2 in the square root. And there's our product. Okay. So try number 4 on your own, and then you can check your answer here in just a bit. So check to see how you did there. If you got 12x square root of 14, that's very good news. Then you're on the right track there. You can see the work. You can multiply the interior with interior, 56x squared. 4 goes into that, so you can pull that, and of course x squared is a perfect square, so we can take the square root of those. The 14 is unfortunately going to have to stay inside, but the square root of 4 and the x can come out here and be multiplied and cleaned up. So this is your solution. See if you got that one okay. All right, now let's talk about things that look like this when they don't have an addition symbol in the middle, and then we'll talk about when they do. So, or subtraction sign. So if you've got this whole thing in parentheses raised to the second power, and the term is one monomial, right? One full term here. There's no pluses or minuses. Then, yes, you are allowed to distribute that. So you have essentially option 1 here. So option number 1 is simply to distribute that exponent and just say I'm going to square this and I'm going to square that. So that's going to be 3 squared times the square root of 10 squared. Well, 3 squared is 9, and the square root of 10 squared, basically these two operations just cancel, and we just end up with that 10. And of course, then we get 9 times 10, which is just 90. So that's one way to tackle that problem. Okay. Option number 2 is to just expand it, which is what's really happening. That might help you visually a little bit more. Is basically if we have 3 square root of 10 to the second power, that really means 3 square root of 10 times another 3 square root of 10. Okay. And then once again, you sort of multiply the like things with each other. So if I've got outside with outside, those can be multiplied together. And then interior with interior, those can be multiplied together. We'll end up with 9. And then here it'll be square root of 100, which happens to be a perfect square. So it'll be 9 times the square root of 100, which is 10. And guess what? That still gives you 90. So you decide which one you like to think of it better. The only catch is that this always works. Expanding it out and then seeing what you have there and proceeding is always going to be a good visual option. It always works. The distributive concept, it only works when it's all one term together. So it will not work in a little while when we have, for example, something times itself to the second power, that kind of thing. So just keep that in mind. Try number 6 and see if you can successfully get that one. Okay, so if you just use the distributive option like number 1 here, you would have squared the 2, which gives you squared the square root of 7, which is going to cancel. So you end up with just 4 times 7, which finalizes out to just 28. There you go. Okay. All right. Now, what if we have stuff that looks like this? Well, if this is kind of like giving you flashbacks to distributive property, then you would be absolutely right. That's exactly what you would do here. You're going to distribute what's on the outside of the parentheses to each of the terms. So it's all about the distributive property here. However, just keep in mind that you can really truly only multiply inside with insides, or like outside numbers with outside numbers. So here, for example, the square root of 5 times 4, which is a whole number 4, we can't actually make that into a 20, although it would be nice. We literally just have to leave them right up next to each other, because they're not really, that's not really a 5. That's the square root of 5, which is, like we said before, an unpleasant long decimal. So you got to make sure that you don't actually perform the multiplication if it's a whole number with the radical. You just leave them next to each other. Now, in contrast, when I go to do the second distribution, these are both radicals and we can multiply them together. So there we can do 5 times 8, which gives us 40. And then make sure they're simplified. So this is not simplified. I'm sorry, this is fully simplified, but this one is not. We know that we can break that up into 4 times 10 and take the square root of the 4, which is just 2. And this one was already as simplified as possible. And then, of course, like last time, we checked to see if they're like, because we might actually be able to add it and be done, but these are not like radicals, so that is as far as we can go. There it is. Okay. Let's try one more like that, and then you can try number 9. Let's do this one together. If we distribute here, these are both interior or radicans. They're both on the inside, so we definitely can multiply that together. 5 times 15 is 75, and then that has that y. Plus, but then when we multiply by the 4, that's a whole number 4. So we leave the radical just right next to it. We don't actually multiply that together. And then we want to make sure that these are simplified. Like we said before, this is already 5 and y. That doesn't have any perfect squares or anything like that. So this is just going to come straight down, just like this one came straight down. But here, there's a perfect square there. I hope you catch it. 25 goes into 75 3 times. So we can split that up into 25 times 3, and then the y, and take the square root of those. So the square root of that 25 comes out, and it's a 5. The 3 and the y are not perfect squares, so they're going to stay sort of stuck inside, and then we just bring this one down. That was already as simple as possible. Always check to make sure, are these like radicals that we could add? If so, add them together. If not, you're finished. Okay. So try number 9. See if that one works out well. And we can answer here. See if you got 2t square root of 3 minus 2t. If so, then I think you are rocking and rolling. We distribute it, we get 12t squared. And in the other term, we get 4t squared, which the whole thing is a perfect square that can all come out. Square root of 4 is 2, square root of t squared is t. Here, not everything is going to be a perfect square, but a lot of it is, right? 4 goes into 12 times 3, and the t squared. So sometimes I like to group them together. I think we've talked about this. Put those perfect squares together, and the stuff that is not a perfect square that we're not going to be able to release out of the radical, and then just take it from there. The square root of 4t squared is 2t. This stays in. And of course, like we said, this one was perfect. So that is as far as we can take that. So we've got some distributive property. If this starts to feel a little bit like the work that we did with polynomials, you are not wrong. That is accurate. There's a lot of similarities here, including FOIL. Here we go. So you've got a couple of products here, but they're both sums and differences. So technically, these are not polynomials, but the behavior and the work we're about to do is exactly the same idea. When we've got two terms, right, that are added or subtracted times another two terms, we are still going to think of this in terms of FOIL. And I always say this, right, I use the word FOIL, but you could use the box method, the vertical method, the distributive method. I just call it FOIL for short, but I gave you lots of options, and you can always use the one for the multiplication that you like the best, right? But I do like FOIL, so I am gonna FOIL this, right? So if I start with this first term and I make sure that I do the first two terms and the outer two terms, that's really just distribution. I do 2 times 7, 14. And then 2 times the square root of 5. Again, those are not like numbers, so I'm just putting them next to each other. And that would be positive. Okay. And then when we go in to do the inner terms and the last two terms, that's really just distributing that negative square root of 5. So a negative times a positive is a negative here. These are a radical with a whole number, so we'll leave them next to each other. And then on the next one, positive and a negative is still a negative, but here they are both on the inside, so I can multiply that, and I'm going to get the square root of 5 times 5, which is 25. Now let's see what, if anything, we can clean up here. We can definitely combine these like terms. The 14 is here. Positive 2, this is what we did last time, adding and subtracting. Since these are like radicals, we can add them. We cannot do this one yet, but these we can add, so, or subtract. So a positive 2 and a negative 7 is a negative 5 square root of 5. And then minus the square root of 25 is actually a perfect square, so that becomes a whole number. Now that it's a whole number, now the game changes, because these guys are like terms, and I can do 14 minus the 5. So I can combine the whole numbers here, and you really just get 9, and then that negative 5 square root of 5. So that's our final result here. Okay. We'll do one more like that. Let's try this middle one here. You've got 3 plus the square root of 2, and then square root of 2 minus 4. So let's try this one. Okay. Whatever method you like best, like I said, you can, if you want to think of it in terms of distribution, FOIL, the box method, either way, you just end up distributing the 3 and making sure it gets multiplied by both, and then distributing the square root of 2 and making sure that one gets multiplied by both terms here. So when we do the first one, 3 times the square root of 2 just stays 3 square root of 2. Okay. 3 times negative 4 is just a negative 12. And then we go to our inner terms. Here in the middle, we end up with the square root of 2 times the square root of 2. That's the square root of 4. And then square root of 2 times a negative 4 is just negative 4. Square root of 2, those have to stay side by side because one's a radical, one's a whole number. We do know, though, that the square root of 4 is just 2. So this can clean up to just a nice whole number 2. And that kind of lets us see more clearly what our like terms are that we might be able to combine. We have like radicals here. So we've got a positive 3 and a negative 4, and they're both square rooted to 2, so we'll be able to do that. And then we've got these constants, or these whole numbers, negative 12 and 2. So negative 12 and 2 is negative 10, and then 3 and negative 4 is negative 1 square root of 2. So whether you put the 1 there or not, this is your result. All right, so then let's really move on. That's good practice on the multiplication. Let's really talk about simplifying the quotient, and that really means, you know, dividing if we can, and then simplifying those radicals, and then this new player, which is all about not leaving a square root in the denominator. So 13 is a really good example of this. We can definitely check and should check that this doesn't reduce 3 over 5. If they're both on the inside, we can divide them if they were divisible. But they're not here. 3 over 5 doesn't simplify or reduce. Neither of these guys have a common factor. So the next job is to make sure that we don't leave a radical in the denominator. So I want to multiply this by something so that I get a perfect square. That is our goal. Okay. And for square roots, a lot of times, not always, the easiest thing to do is just to multiply that denominator by itself. Because in doing so, it's going to guarantee us a perfect square. So on the top, square root of 3 times the square root of 5 is square root of 15. But more importantly, on the bottom, it's 5 times 5, which is a square root of 25. And that's a perfect square. That lets us clear that denominator to a whole number 5. And that's called rationalizing the denominator. And you must do it anytime you have a radical in your denominator. So this is the simplest version of this problem. Okay. You cannot divide this because, again, this is on the inside and this is on the outside. So these are not, you could have if they had been like this, but one's inside the radical, the other one's not. So that cannot be simplified. 15 doesn't have any perfect squares in it that we can pull, and we did not leave a radical in the denominator, so we are safe here. We're good. Okay. All right. Let's do a couple more like that, and if we are okay, then like this one here, 3 is pretty simple. These don't go in. I know if I just multiply by the square root of 3, that'll take care of that radical. So on the top, I'll get square root of 33 over the square root of 9, but the square root of 9 is just 3. And so that would be our final answer. And 3 is number, no radical. 33 does not have any perfect squares. It's just 3 and 11, so nothing to worry about there. You are fully simplified. Now look at number 15, because 15 is a good example. Yes, we could multiply by 32, and that will work, but it's going to give us some pretty big numbers. It doesn't always have to be multiplied by itself. We really just need to multiply by something that'll guarantee us a perfect square. So although I could multiply it by itself, if I just wanted to kind of be done with it, I think it's actually easier to think about the fact that 64 is a perfect square, and all it requires for me to get there is just to multiply this by 2. So since I know 32 goes into 64, that would take care of what I need. So it does not always have to be times itself. Okay, my goal is a perfect square. So I know that 32 goes into 64, and that all I have to do is multiply by a 2 to make that happen. I also have to watch out for the variables, though. I need a perfect square there as well. So I need to also make sure that I multiply by a b, so that when I do this, I get b times b, which is b squared. I need to get a perfect square every time. Okay, if we do that, once we decide what we're multiplying by, we make sure we do it on top and bottom. And as a result, let's find out what we get here. 5 times 2b is 10b inside that radical on the top. But more importantly down here, 32 times 2 is 64. And b times b is b to the second. There's my perfect square. That's the goal. And so in our numerator, we get square root of 10b, which we're pretty confident doesn't simplify. On the bottom, we can take the square root of both of those things and just make it 8b, and you're done. Again, we cannot reduce that. I know it's tempting. Don't do it. If one's inside a radical and the other stuff isn't, you cannot simplify it. Okay? All right, so here's another good example, number 16. We might just finish with that one. Here's another good example of where you don't necessarily have to multiply by itself. Well, you could, but then you're going to have to do a little bit extra work later to reduce and simplify. 8 is not a perfect square, but if I think about what's the easiest, shortest, sort of smallest, I should say, perfect square that 8 goes into, I can come up with 16. You know, so I'm like, oh, I can just make this a 16 if I just multiply it by the 2. So I'll just do square root of 2. That'll take care of that for us. Okay, so if we rationalize with a square root of 2 on top and bottom, on the top we get square root of 10. On the bottom we've got 4 times, so the 4 is a whole number, it's still there, and then 8 times 2 is 16. Right? But wait! Square root of 16 is a perfect square, right? So then we can say 4 times the square root of 16, which is also 4. And now those two things can be multiplied together. So in the end, we've got square root of 10 over that 16, like that. Okay? That's the shortest, easiest way. Could you do it another way and just multiply it by itself by 8? Yes, you could, but then you'd have a little more simplifying to do. Okay? So I think those are some good examples. Let's go ahead and finish out with one of our word problems here. We've got an electrical current in amps that can be represented by square root of W over the square root of R, where W is the power in watts and R is the resistance in ohms. How much electrical current is running through a microwave oven that has 850 watts, so there's our W value, okay, and 5 ohms of the resistance. So there's our R. Give the answer in simplest form and also estimated. Okay, so we just need to take this formula here, insert the values that we're interested in. So this microwave has a wattage of 850 over a resistance of 5. They're both squares, so since they're both square roots, if this reduces, you can definitely do that. And I have a feeling 5 goes into 850. So let's see, if I try to simplify this, since they're both inside of a radical, we can simplify. Hey, that reduces just to a nice, easy 170. So this is square root of 170, okay? And that's our amps. And then they ask, give the answer in simplified radical form and estimate it out. So let's go ahead and take care of that estimated, because that's usually a little faster. If we take the square root, we're looking at to the nearest tenth, so this would round down, so just stay at 0. So 13.0. There it is. This, well, let me think about what this breaks up into. It really breaks up into 17 and 10, and then 10 is 2 and 5. I really don't think that's going to have any perfect squares, but you can always check by putting that into that trick that I showed you guys in the calculator and checking. But really, these are the only two factors. Well, and 2 and 5. Yeah, that's not gonna have any perfect squares. So this is really as simplified as it gets. There it is. And we'll do number 20 together in class tomorrow as kind of our warm-up. So that's your notes for multiplying and dividing.